Hi dear students, welcome to Gate Wallah. This is 𝐂𝐨𝐻𝐿𝐴, Faculty of Measurements and Instrumentation. In our previous lectures, we have seen the power measurement by using the dynamometer. Now in this lecture, I am going to talk about the 2 wattmeter method. So by using the 2 wattmeter method, how to measure the power for the 3-phase especially. See, one of the important topic with respect to gate examination and also non-gate examinations. So definitely many number of times the questions are coming in this topic. So let us go through today's agenda. I hope all of you are following these YouTube classes regularly. So please maintain a short notes, regularly following the notes, and please practice more number of questions at the end of each session. According to the topic, you please try to practice the PYQ. Whatever the concepts I am discussing, these all concepts are regularly asked concepts. So practice accordingly. Now, today in one shot, I want to talk about 2 wattmeter power measurement. Okay, so coming to the agenda today, first of all, we should know what is a 3-phase power and what is the necessity of 3-phase power. And in 3-phase power, we are having the star model and delta model. So we will talk about 3-phase star delta model first. And we have certain relations with respect to line current, line voltage, phase voltage. And after that, one of the famous theorem, Blondel's theorem, which is related to the 2 wattmeter method. So that we'll discuss, and after that we'll start a derivation on the 2 wattmeter method and we'll derive the formula for the power factor. So, and next we'll follow the numerical problems related to the 2 wattmeter. So first, let us start with 3-phase power. Okay, hello. Hello. Yeah, sorry. Let us start with 3-phase power. So what is the necessity of 3-phase power and why it is more advantageous over the single phase power? So that we will discuss here. So before discussing that, just in our dynamometer, we have seen, in the dynamometer what we have seen, this is our dynamometer, single phase power measurement. If you see single phase power, what we have done, we have taken a current coil and we have taken a load and we have taken a moving coil like this. So now this is the single phase AC supply. But in single phase AC supply, we are using the dynamometer. So you will be having a question, sir, by using the dynamometer, we are using the single phase power now. So why is the necessity of 3-phase power? Remember always the single phase power, what is the formula for the single phase power? That is a VL IL cos phi, yes or not? So that is the reading by the wattmeter. But remember, the single phase power measurement, is majorly for what? The single phase power measurement is majorly for domestic applications. It is majorly for domestic applications. But if you want to go for 3-phase power, 3-phase power is basically for industrial applications. It is industrial applications. Industrial application demands more power. Yes or not? So comparatively single phase power, the 3-phase power is having certain characteristics. What are the characteristics? So what are the advantage of 3-phase power? So why 3-phase power over single phase power? If you check, why 3-phase power over single phase power? If you check, so the 3-phase power is having more amount of amplitude of voltage comparatively single. Yes or not? So more voltage. Second point, the transmission of the signal is economical. Transmission by 3-phase in 3-phase is economical. Because if you want to use the single phase meters 3 times, how many coils and how many copper windings and how many conductors you require, that you compare with the 3-phase power, they are very, very less. So The major point is transmission in three phase is economical because we need less number of conductors. Conductor means copper. So losses also less, budget is also less. So in that way, the transmission of three phase is economical. So in that way, they are found as one of the best application when you want to transmit the power over a duration. Second, over a long duration. Okay. Second thing and third thing, if you observe in three phase power, we are having the rotational magnetic field concept. Yes or not? RMF, rotational magnetic field. If you see the windings, we are having the rotational magnetic field concept. So this particular rotational magnetic field concept is used for the self start of the machines. For the self start of the machines. Yes or not? But in single phase, we don't have that facility. In single phase, we don't have the rotational magnetic field concept. So that's why auto start is not possible. Auto start is not possible. Next and most important point here is the DC curve. DC curve, that means after rectification. DC curve of three phase power. DC curve of three phase power. Three phase after rectification. After rectification is a smooth. Yes or not? Comparatively single is smooth. The smooth means what? Low power, low ripples, the low ripples. That is most important, low ripples. So in three phase power, once you convert into DC, the DC curve is so smooth comparatively the DC curve of single phase. That's why we are getting the low ripples. You understand? So these are the major features. Okay, so voltage of the three phase will be more. More voltage is possible in three phase compared to single phase. That is a major advantage. And transmission of power in three phase is economical. That is second point. Next, three phase power contains a rotatory magnetic field. So this rotatory magnetic field, what it will have, this will be most important in the self-starting machines. In single phase operation, there is no concept of rotation magnetic field, so there is no question of the self-start. Next, DC curve of three phase after the rectification is smooth. So these are the fundamental typical points. That is the reason in industrial, we are not dependent on the single phase, we are going for the three phase. That's why in three phase power measurement, what are the instruments we have to use? As we are having the dynamometer, wattmeter, sir, you may be thinking that this is for single phase. So I will be going for 3 dynamometers so that I can measure the three phase power. But remember, the most important point I want to write here is three phase power is equal to 3 times of single phase power. That means three phase power quality is equal to 3 summing of single phase power. But the vice versa is not true. Vice versa is not same. That means if you club the single phase power 3 times, the quality of the power that you are getting, may not be exactly equal to the three phase power characteristics. That is the reason why we are going for, by considering all these features, this 1, 2, 3, 4, 5. So these are the major features why three phase power is used. Okay, so please try to understand these 5 points that may be expected. Why? Because for electrical students and instrumentation students, in interviews this is an expected question. Why three phase power? What are the features of three phase power? A three phase power having certain advantages over the single phase power. In industry we require more voltage. That's the reason we are going for. So when you compare three phase, what are the features of the three phase and what is the order of the three phase? Okay, so what do you mean by three phase? They may be having the equal amplitude, equal frequency, equal magnitude of voltage, but their voltages are shifted by 120 degrees. Okay, so what do you mean by a balanced three phase system? A balanced three phase system Balanced three-phase system means what it is having? It is having equal magnitude of voltage, frequency of voltage, equal frequency of voltage, equal amplitude of voltage, and equal magnitude of impedance in all the phases, and type of impedance is also same type of impedance, So these are the basic features of what we call as balanced three-phase system. In a balanced three-phase system, it is having the equal magnitude or amplitude of the voltage, frequency same, but the three phases are shift by 120 degrees each. That means if you take three phase, 360 degrees by n, so that is a 120 degrees phase shift is there between these particular things. So if you see that sequence, that is what we call as RYB sequence. The sequence is important. So these are red, the white, the blue. So they will be having a RYB sequence. So if I want to show you in the form of waves, so this is our graph. So first example, if you take the red waveform, next the Y waveform is having a phase lag of 120 degrees. Next the blue is having a phase lag of 240 degrees, like this. So if you see this, all the amplitude are same here. If you see this, all the amplitude are same. This amplitude, all the amplitude, sorry, last one, redraw. Yeah. So if you see this, all the amplitudes are same. You see the amplitudes. So this is a VR. So this is a VR, the VY, the VB. So this is lagging by 120 degrees. Okay. So comparatively VR, VY will be having a phase shift of 120 degrees. Okay. That means VY lags VR by 120 degrees, and this is lagging by 240 degrees. Okay. Or if you take the leading relation way, so it is going to be like this. For example, if you draw here, so it is leading by 120 degrees. See, that is the waves you have to understand. So VR, VY, VB. So the voltage of VR, so suppose if you take the VR voltage as Vm sin omega t, the Vy will be Vm sin omega t minus 120 degrees, or Vb can be taken as Vm sin omega t minus 240 degrees, or we can also take it as 120 degrees. So there is a phase shift of 120 240, but if you see with reference to this, so here there is a phase shift of 120 degrees, but it is leading by 120 degrees. Vb is leading the Vr by 120 degrees. Each is having a phase shift of 120 degrees to each. Comparatively, Vy is having a phase shift of 120 degrees. That means Vy lags Vr by 120, Vb lags Vy by 120, but Vb leads Vr by plus 120. That means Vb leads Vr by 120. Okay, so what I can write here, in three phase, Vy lags Vr by how much degrees? 120 degrees, whereas Vb leads Vr by 120 degrees. That's what I'm mentioning here. Vr is equal to Vm sin omega t, Vy is equal to Vm sin of omega t minus 1. That we can represent with reference to the waveform also, with reference to graph also, with reference to the graph also. So with reference to graph also we can represent. With respect to graph, how it will be, just let me take. So if we take this as our Vr, then this will be our Vy, then this will be, so this is our Vr, Vy lags by 120, this is Vb leads by, that is a graphical representation of a particular. And remember, in three-phase power transmission, definitely we follow two models. One is the star model and delta model. So actually I am taking the separate slides. Okay, I am taking the three-phase star model. We have a gap. Right. Basically we are having the star model and delta model. In star model, how they are connected. Okay, so if I want to show in a star model, if you consider, these are the inductors, inductive load I am taking. So three coils, connected like this. So let us take this as R, Y, B. R, Y, B, and let us take this in. So this is a three-phase star model. So now here, if you see the current passing through this is IR, and here if you take the phase current, this is the IRN, and if you take this is the IY, and the phase current here traveling, that is the IYN, and if you take this is the IB, and the phase current that is entering is IBN. Okay, so in a star model, we are having certain terminology, line voltages, phase voltages, line currents, and phase currents. So this is a star model, three inductors or three coils are connected. Of course, it is a lagging power factor, we are taking the coils. For a leading power factor, we can go for the capacitor. Okay, so now if you see this particular voltage, whatever is there, this voltage, we take this particular voltage, we can take it as VRN. And this one VYN. and this one VB, VRN, VYN, VBN, and this one now I can take it as line voltage VRY, and this is VYB. Reference to this, if you take, I'm taking this one is our VBR. So now you got the clarity. Okay, so let me remove this picture so that there will be no. I will do one thing. I will cover with this. Okay, now let us see a three-phase star model. I think it's gone. A three-phase star model, how it works. Let us see once again. Sorry, this one. Take a Let us take this like this. Okay, so this is our R N, our Y, our B. Clear? So this is the three phase. I will take this as the R phase. This is our Y phase. This is the B phase. So in star model, the loads are connected in a star way. So this is the, I can take is a load impedance ZPH. This can be leading or lagging. So right now I am considering ZPH. So now if we check with respect to neutral, so this is a neutral. So if we consider this as IR, this is as IY, this as IB. Okay, and the voltage here I can take it as the VRN, that means voltage across the impedance, and this one I can take it as VYN, and here I can take it as VBN. VRN, VYN and VBN. Okay, so and the voltages between the line, that is the VRY, and this is VYB, this is VBR. Okay, so that is the situation. So now if we check this, what is this? VRN, VYN, VBN. So these all are phase voltages. Phase voltages. And between the lines, whatever we are taking, phase voltage means what? That is a voltage across the impedance. That is the point you have to understand. So this is what? This is a voltage across the impedance. Voltage across impedance. Next, what is the line voltages? VRY, VYB, VBR. So these all are voltage, line voltage, voltage between the lines, voltage between lines, voltage between the lines, VRY, VYB, VBR is the voltage between the lines. Try to understand. Next, if you see the color, let me take IR, see the currents which are entering into the impedance. This is IRN I will take, this is IYN I will take, and this is IBN I will take. So IRN, IYN, IBN, these are called phase currents, whereas IR, IY, IB, these are called line currents. In network theory, you could have studied the relation between the line voltage and the phase voltage and relation between line current and phase current. Here we are not going to that derivations. Okay, just we'll see the characteristics and we'll move to the three-phase power measurement by using the 2 wattmeter. Our motto here is to measure the power, and these are what? These all are phase currents and line currents. If we observe the thing in star model, the IL is equal to IPH, VL is equal to √3 VPH. That I am not discussing here, that is a part of your network theory. So what are the features of star model? The features of 3-phase star model is dash. There are certain 3 points here. The first point is the line voltage will be √3 times of phase voltage. Second, the line current and the phase currents are equal. So this point, that also you have. Next, Coming to the delta model. So how a delta model will be looking like? So for delta model, we have to take like a triangular, like a delta. So this is our okay. So this is a situation. So let me take the line, the R line, Y line, or B line. R, Y. This is what we call as ZPH, ZPH. Clear? And the voltage, so this is our current IR, and let's take this as R, Y, B. So if you take this is the IY line and this is the IB. Okay now. So how to understand the currents now? The currents are splitting here. If you check IRY, IYB between the currents, between R and Y, we can take the IRY. So this is IRY. And this is IYB. And this is IBR. Okay. So what you can understand here? What are the phase voltages? The voltages across this particular impedances. The voltage across the impedance, these are the VRY, VYB and VBR. VRY, VYB and VBR. These are the phase voltages, and line to line voltage is also same, right? So these are VRY, this is a VYB, and this is our VBR. Next comes here, line is also same, VPH and VL both are same, whereas IR, IY, IB, these are the line currents. IRY, IYB, IBR, so these are the phase currents. So try to understand, there we are having, in star model we are having IL is equal to IPH, but here if you check, IL is not equal to IPH, but VL is equal to VPH. The voltage across the impedance, that is, and the line voltage both are same here, but the line current and the phase currents are not same. Okay. So in the delta model, in star model and in delta model, what you can observe? Just opposite. Yes or not? So here VL is equal to VPH. So the features, let me write the features before entering into the Blondel's theorem. Let me write the features of the delta model. The features of three-phase delta model. What are the features in three-phase delta model? The first point is line voltage and the phase voltage both are same, but the line current and the phase current both are not same. Both are. So please remember these points clearly. because they are suitable and they are useful in solving the problems related to the wattmeter. So keeping this in mind, now we'll move to the 2 wattmeter method. What is the necessity of 2 wattmeter? See here, in 3-phase power, suppose if I want to measure the power measurement in star model, how many wattmeters are required? As you want to measure between this R, Y, B, N sequence, that means a 4-wire 3-phase but 4-wire, because you are having the neutral. In that is a situation, 1 wattmeter can be connected between R and N, 1 wattmeter in Y and N, 1 watt with V and N. So 3 wattmeters are required. But if the neutral line is not present, then what we can do, we can keep one particular line as common line and we can adjust the 3-phase power measurement by using the 2 wattmeters. So that's what the next content, which is called as the Blondel's theorem. So before entering into the next content, let me brief out what we have discussed till now. What we have discussed till now, we have started about what is the 3-phase power. So this is a single phase AC power. So to measure the single phase, we need the 1 wattmeter is required. But when you are going for the 3-phase, why you are going for the 3-phase? That's the first question. The reason for the 3-phase power is, in 3-phase power comparatively greater than single phase, yes or not, the voltage magnitude or whatever that voltage signal you are getting, comparatively single phase, that is more. Next thing, transmission in 3-phase is economical, that I was already told you, and 3-phase power, the advantages of 3-phase power I have explained you. In the next slide, what is a balanced 3-phase system? Because especially instrumentation student, they should be aware of these words: balanced 3-phase, unbalanced system, symmetrical, asymmetrical. Balanced 3-phase system means what? Equal magnitude of voltage, equal frequency of voltage, equal amplitude of voltage. Of course, magnitude amplitude same. Equal magnitude of impedance. Even the impedance also should be equal. And the type of the impedance is also same. Type of the impedance is also same. But the most important point is their phases are separated like this. The phases are having a shift of 120 degrees. So VR, VY, VYB. So VR, VY, VB, if you check, VY lags VR by 120, whereas VB leads VR by 120. That's what I have shown you with the diagram also. And now, if you take the most famous models in 3-phase power to transmit, the star model and delta model. In the star model, the 3 loads are connected in a star. Exactly at the center, there is a neutral, and we are having the lines. So this is the current passing through the line, and this is the current passing through this line. So this is IR, IY, IB, and these are the line currents, and the currents which are entering to phases, these are the phase currents, and the voltage across the impedance is the phase voltage, and the voltage between the lines is the line voltage. Okay, so I have given you the terminology. VRN, these are called voltage across the impedance, these are called phase voltages, and these are called line voltages, and these are called phase currents and line currents. And we know very clearly that from the network theory, the line voltage is having √3 times of VPH, IL is equal to IPH. In star model and in delta model, this is the common difference. In star model, line current is equal to the phase current. Next, if you see the 3-phase delta model, in 3-phase delta model, we are having the line voltage, line current, and like this. But if you see here, the line current and the phase currents both are not same. So this is IR and this is IRY, but whereas this is IY and this is IYB. So this is IB and this is IBR. So line current and phase currents are not equal in the 3-phase delta model. But what are equal? If you check, the line voltage means between R and Y. Now the voltage that we are taking is also VRY. So the voltage across this impedance, so that also I want to express here. The voltage across this impedance, that is the phase voltage VRY, and the voltage across this I can take VYB, and the voltage across this I can take it as R. So VRY, VYB, VBR. So these are called phase voltage, and the phase voltage and the line voltage both are same. But the line current and the phase currents both are not same, because the IR is entering and split into 2 parts. So by the current division, we can get a relation. So the relations are this. The features of three-phase delta model is VL is equal to VPH, just opposite to that, but here the line current is root 3 times of the VPH. So this is what our content. Okay, dear. I hope all of you understood. And now, what is the 2 wattmeter concept? Why we have to go for 2 wattmeters? So that we will discuss with the Blondel's theorem. So there is a statement I want to taken from the standard books. What is Blondel's theorem? Just go through the statement. If a network is supplied through n conductors, so how many conductors? So let me highlight this. So let me highlight this n conductors, or let me write like this. Visible clearly? N conductors. N conductors. Number of conductors. It can be 3 or 4 or 2 or 3. If a network is supplied through n conductors, the total power is measured by summing the readings of n wattmeters. Yes, if you are having 3 phase, then 3 wattmeters are required, provided so arranged that a current element of a wattmeter is in each line and the corresponding voltage element is connected between that line and a common point. If common point is located on one of the lines, then the power may be measured by n-1 wattmeters. So how to understand this concept in detail, that we are going to discuss in the next. If you are using a neutral line, then current coil is connected to each line, and in between the current coil and this neutral, you are connecting one potential coil, then definitely you require n number of wattmeters if it is a n connection supply. But if the neutral line is not present, one of the line only is taken as a common point, then n-1 wattmeters are required. That's what the statement. Once again, please go through. If a network is supplied through n conductors, the total power is measured by summing the readings of n wattmeters. So arranged that a current element of a wattmeter in each line and the corresponding voltage element is connected between that line and common point. If the common point is located on one of the lines, then the power may be measured by n-1 wattmeters. Got it? That means what? What I want to say, see here. What I want to say here, yeah, if you see this diagram, if I am using this neutral line, then definitely I am having the 3 phases. So I require 3 wattmeters. Wattmeter 1 between the R and N, wattmeter 2 between Y and N, wattmeter 3 between B and N. Then definitely by taking the 3 readings of the wattmeters W1, W2, W3, those 3 can be added and we can take the result. Okay, W1 plus W2 plus W3. That means what? In a system of RYBN, where is a neutral line is present, RYBN, then definitely we require 3 wattmeters. Suppose this neutral line is not present. In the place of neutral line, we are taking one line only as a common line. We are taking one line as a common line. That means 1 wattmeter can be connected between this and other wattmeter between these two. Then n-1 wattmeters are sufficient. That means 2 wattmeters are sufficient. How that is possible? That will prove now with the derivation. Okay, so this is the Blondel's theorem. So now I want to talk about symmetrical 3-phase balanced 4-wire system and symmetrical 3-phase balanced 3-wire system. So how to understand this? Let me go through. See, I am taking the diagram. Be careful. थोड़ा सा patience होना चाहिए. You have patience. So now this is our neutral line. So this is our R, our Y. So what to do now? Symmetrical 3-phase balanced 4-wire system. So if I am taking a common line for the neutral, so one line I am taking for. So what I can do to measure the power in one phase, what I require? I require a wattmeter. That wattmeter should have one current coil and one potential coil. So the current coil is in the line connected here. So one current coil I am taking here. The other potential coil I am connecting. Similarly, let me draw the diagram now. Fatafat. So this is the current coil and this is the potential. So now this is going to become 1 wattmeter. Okay, next. One current coil here and one potential coil connected to line. So this is another wattmeter which will give the phase voltage between the Y and the N. And the last one here, one current coil and potential coil, again I am connecting. So now if you check, so this is now 1 wattmeter. This is a second wattmeter. This is 1 wattmeter, second wattmeter, third wattmeter. So this is the wattmeter 1. So we can take this as the IR, we can take this as IY, we can take this as IB, and the voltage between this is the VRN, VYN, VBN. So if you see this picture, it is a balanced symmetrical 3-phase but 4-wire system. How many wires are there? 1, 2, 3, 4 wire. So this is what we call as wattmeter 1. This is what we call as wattmeter 2. This is what we call as wattmeter 3. So these are the voltages I can take. VRN, which is our ZPH here, and this is another ZPH. So we can take this voltage as VYN, and this is a ZPH. This voltage we take it as VRN, VYN, and VBN. These are the phase voltages. Okay, and the phase currents passing through this IRN, IYN, IBN. Line currents IR, IY, IB, and the voltages here. If you see, we want to see, now we are connected between 3 phases now. So these are VRN, VYN, VBN. So we are getting the 3 phase voltages. Okay, so by using this wattmeter, I can measure the VRN, comma IR reading, and by using this, I can measure VYN and IY reading. Like that, 3 phases, 4-wire system, definitely by using the 3 wattmeters. So the total power here is equal to W1 plus W2 plus W3. Okay, the reason is Here your W1 will give you VRN, IRN cos phi. W2 will give you VYN, IYN cos phi. That means we can take W1, W2, W3 like this. W1 is giving one phase, W2 is giving the second phase, W3 is giving the third phase. So W1 is giving the VPH, IPH cos phi. W2 will give again VPH, IPH cos phi. W3 will give you VPH, IPH cos phi. So altogether the total sum is the total three phase power by the wattmeters. 3 wattmeters have used, so I can use the 3 wattmeters. This is 4-wire system. Remember my dear, 4-wire system means we are having the R, Y and N. R, Y, B and N. Along with the 3 R, Y, B, there is one more line, that is a neutral line. You understand? Now with this understanding, now we'll move for symmetrical 3-phase balanced 3-wire system. So clear na? Any diagrammatical difference? You got it? Yes, perfect. But what is happening here? How many number of coils are used? So if you see the 3-phase 4-wire system, symmetrical means balanced, 3-phase 4-wire system. 4-wire means what? R, Y, B, N. How many wattmeters? Wattmeter 1 is having 1 current coil and 1 potential coil and 1 series resistance. Wattmeter 2 is having 1 current coil, 1 potential coil, 1 series resistance. Wattmeter 3 is having 1 current coil, 1 potential coil, 1 series resistance. So total number of components 3 plus 3 plus 3, 9 components. 9 components are used in the wiring, and definitely the number of wires also high. So according to Blondel's theorem, what the Blondel's theorem says, where you are using the 3 devices, 3 wattmeters you are using, instead of 3 wattmeters, you can go with a less number of wirings and less number, you can reduce it to 2 wattmeters. So that is what the next point, the 2 wattmeter by using the RYB. So how it is possible? What is the RYB sequence? That means there is no neutral. Now in that common point we are taking one line, either Y or B, and we are connecting the wattmeter. So that we will discuss. Chalo. Now we'll start the 3-phase balanced 3-wire system. How it looks like? If you see the 3-phase balanced system, I am taking a star model. There will not be any common line. Okay. So we can take this now, 3-wire system. How it is a 3-wire system, I will let you know. So let us take the order as R, Y, Z. Yeah. So this is R, this is Y, this is B. I am taking R, Y, B sequence. So here I am not using the neutral. then the current passing here will be IR, this will be IY, this will be IB. Okay, so for neutral I am not having any line. Okay, so then if is the situation, we call it as 3-phase 3-wire system, RYB. So now if I want to measure the power by using the 2 wattmeters, I can connect 1 wattmeter between this R and B and another wattmeter between Y and B, so that I am going to measure the 2 wattmeter readings. So I will show you that in the next diagram, coming diagram. But by using the 2 wattmeters, we can measure the symmetrical 3-phase 3-wire system, but it does not have any imbalance in neutral line. Okay, so how it is possible? So according to the Blonder's theorem, I can connect 2 wattmeters method, which will have W1 plus W2 will be giving the 3-phase reading, 3 VPH, IPH, cos phi. Okay, so that how it is possible, let us see now clearly. Actually, when you are connecting the load, always remember the load can be lagging type or leading type. So that's why to explain this connectivity of 2 wattmeter method, there are 4 possibilities. The 4 possibilities are 3-phase star model with a lagging power factor. Lagging power factor means that is nothing but inductive load, because in inductive the current lags by 90 degrees. Similarly, 3-phase balanced star model, leading power factor means capacitive load time. Similarly, we can go with the delta model. So just in this class I will be explaining the different one possibility. Okay, so 2 wattmeter models, we can call this as 2 wattmeter method models. Okay, so first let me talk about 3-phase star model lagging power factor. Okay, so I want to explain 3-phase star model lagging power factor. Power measurement by 2 wattmeter. How it is possible? Let us go and see in a systematic way. Okay, so now I am going to draw the diagram. So this is our star model. Have patience. So let us take this as ZPH. Hello, voice clear? Hello, yeah. Now see here, how I am going to use 2 wattmeter method in detail I will explain. So here I am taking the current coil. So let us take this as sequence R, this as Y, this as B. So here comes the current coil, okay, and for the Y, RYB sequence. B. We have some patience to understand this. Of course, at the end conclusions, you can easily take it out, and for examination, those conclusions are important. But to derive, let me follow some procedure. So now, what I am taking here, I am going to take one line as common. I am going to take as one line as common. So RYB sequence. So first, this is the current coil, and here I am connecting the potential coil. So now let us see, this is the IR, this is our IB, this is a Y sequence, this is a B sequence, so these are IY. Okay, now here I am connecting the potential coil. So this potential coil is connected now not to the neutral, this line is connected to a common point, that is B, common point B. So this is what we call as wattmeter 1, W potential. Understood? Is it clear? Current coil is going to this impedance, and the potential coil is connected here, so that I am getting one phase. What is that phase? Between R and B. And the second one, I am going to connect between Y and B. So this is my current coil, and this is our potential coil. Y and B. So if you see now, wattmeter 1 is related to what? The current and the voltage. If you see the voltage, what is this voltage? So this voltage is VRB. So wattmeter 1, okay, before writing that, this is a VRB. So this is, write in the next slide. Clearly try to understand this diagram. I am not using the 2 wattmeters, I am not using the 3 wattmeters, I am using 2 wattmeters. One wattmeter is connected between the R and B, and other wattmeter is connected between the Y and B. B is taken as common point. So now let us check this W1 and W2 reading, how it is going to match with the 3 wattmeters summation. So first of all, what is this IR? So the voltage across this, suppose if you take this N, so this is the VRN as we discussed, and this is our VBN, and this is our VYN. Okay, so this IR, IY, IB, clear. And now if you check the line voltages, this is the VRY, and this is our VYB, and the final, this is our EBR. Of course, we are not taken between B and R. So what are the things I have taken clearly? Wattmeter 1 requires one voltage, and current coil will give you the current, potential coil will give you the voltage. So what is the voltage? That is between R and Y, V R Y, and the current is IR. But most important, we need the angle between this VRY and IR. So this is the most important point that you have to keep it in mind. Next, wattmeter 2 is between Y and B. So this is the VYB. Okay, and the current is IY, and the cosine angle between VYB and, so if you know this particular cosine angle between these two, then we can go for the derivation. So as you know, an important extractions here, we have to get the phasor angle between the line current, and this is also our line current and phase currents both are same in our star model. So just before we have discussed VRN. So let me take this particular line separately. VRN, VYN, next slide here. I hope all of you clear this diagram. Now let me write here an important point. VRN, VYN, VBN, these are phase. VRY, VRN. So VRY can be written as VRN minus VYN. Right? VRN can be written as VRN minus VYN. Perfect. Similarly, VYB can be written as VYN minus VBN, because we have to get these things. So for that, I will go for a phasor diagram. So very clear all of you, VRN, VYN, VBN, these are the phasor voltages. VR, VY, VB, VRY, VYB, VBR, these are the line voltages. IRN, IYN, IBN, these are the phasor currents. IR, IY, IB, these are the line currents. Everything is clear. So here this one is IRN. Once again, please go through this diagram clearly, then only you can understand. This is IBN, this is IYN. Okay. So IRN, IYN, IBN, these are the phase currents. IR, IY, IB, these are the line currents. VRN, VYN, VBN, these are the phase voltages. VRY, VYB, VBR, these are the line voltage. Okay na? So if you want, I can write somewhere, but I am not getting the place. So let me write here. Yes, I will write here. VRN, VYN, VBN, these are the phase voltages. VRY, VYB, VBR, these are the line voltages. IRN, IYN, IBN, these are the phase currents. IR, IY, IB, these are the line currents. Of course, these two are same. Okay. So wattmeter 1 reading is coming between a line current. Yes or not? Wattmeter 1 reading, if you check, that is between the line voltage and line current. So VL, IL, cos. So that we have to get. Okay, let us check now how to get that cosine angle. So for that I am going for a phasor diagram. Okay. So first let me take the phasor diagram of the voltage. So let us take, this is the VRN, this is the VYN, and this is the VBN. So these are the phasor voltages. So these are VRN, this is our VYN, this is our VB. These are the phasor voltages, VRN, VYN, VB. Okay. Now, definitely the phasor currents will be lagging. This is the IRN, this is the IYN, and here comes, okay, so this is what we call as IRN, this is our IYN, okay. IRN is equal to IR, which is nothing but the line current, but whereas this is phase, this is IY, this is IB, okay. So first I want the phase angle between what? First phase angle VRY and IR. So what I want is the power VRY and IR, in between I want, and the second phase angle I want between what? VYB and IY. VYB and IY. First of all, we have to locate the line voltage VRY. To locate the line voltage VRY, we have to take the vector diagram of VRN minus VYN. So this is VRN minus VYN. That means I can write like this now. I can write like this: VRN plus minus VYN, can write like this now. Next, how to write this? This can be written as VYN plus minus VBN. Can I write now? So VRN plus minus V1. That means vector addition of the voltage vectors. So if you see, this is VYN, this is VRN. So what I want here is VRN minus VYN. What is the addition of VYN? So where is the VYN? This is the VYN. So if you take the opposite side, okay, take straight line, so this one, I will take this as clear. I will follow in. Okay, so this is minus VYN, minus VYN. Now, what I want? VRY. VRY means VRN plus of minus VYN. So the resultant of these two, suppose if you take the resultant of these two, the resultant of these two is going to come here. So this is going to be the line vector VRY. Am I right? Yes. So try to understand clearly what I have done. Please follow. So this is my VRY vector. Okay. So this is my VRY vector, which is the resultant of this is the VRY, which is my line voltage. Okay. So what I want now, I want the angle between VRY and IR. So this is the IR. So I want this angle. So first of all, what is this angle? This is 120. Okay na? So this is also 120. When it splits, this is 60, this total is 60. In this, now this is 30. Am I right or not? Listen carefully, my dear. the angle between VRN and VBN 120 degrees, and this cuts exactly 60, and this is 60, and this exactly splits 30. What I want now, I want the angle between VRY and IL, that is this angle I want. Okay, so VRY and IL. So if you take this particular angle, okay na, so this is the angle exactly. This first one. So if you take, this is a phase, we got this phi 1. Clear? Okay. Oh, sorry. A blunder mistake. This is VRY na? No, this is VRB. Sorry, this is VRB na? Please check this. I'm sorry. So this is VRB. VRB, my dear. Check between R and B. This is VYB. See, that's what I'm checking. So now if you see, this is RB, VYB, correct? So here I can take VRY, I can take it as VRN minus, let me check here, 1 second please, all of you listen carefully, we have done a small mistake. Actually this voltage is between R and B, right? The B line, so VRB. So this should be VRB, and this voltage is correct, Y and B, that is a VYB. So VRB can be written as VRN minus VBN. That means it's a vector addition of VRN plus of VBN negative. Similarly, VYB can be taken as VYN minus VBN. So this will be VYN plus of minus. Okay. So now you will get the correct. If you check now, let me check this phasor once again. In this phasor, we want, let me rough this. What thing with this board? Yeah, now let's see. This is the diagram. We have to extract the expression. Yes. Now from the phasor, we'll take the diagram. See, first let me draw the phasor. This is the VRN, the VYN, the VRN is the VYN, VBN, and here comes this is the IRN. This angle is equal to phi, power factor angle we can take. So this is the line current IR. Line current is the phase voltage. Lags. Similarly, you check, these are the currents phasors. Okay, so this is IYN, this is IBN. Current lags the voltage in a lagging power factor. In inductive load, voltage leads, current lags. That's what that was the meaning of the diagram. This is a phasor diagram. So phi, these all are phase current. Phase current is equal to line current in the star mode. Understood? So these all are phase voltages. VRN, VYN, VBN, these are the phase voltages. Now what I want VRB. VRB means VRN plus of minus VBN. So this is VBN. So if you draw the reverse, so this will be minus VBN. Will be minus VBN. Now the resultant of VRN and this I want. What is the resultant? So this is the result. Okay, so the resultant of these two. So that I am going to get the angle between IR and this. So now if you draw the resultant with a green color, this is our, so this resultant is nothing but VRN minus VBN. So this is the VRB. So that is a point you have to understand. So this is our line voltage. Now what I want is the angle phi 1, that is the angle between what? VRB and IR. RB and IR. So that means this one, this angle. What is this angle? If we check, this total angle is 120. This split, it has 60. This splits, this has 60, this has 60. Again, this splits 30. So this is 30. Okay, now I want this one. So what is this angle? This angle is going to become 30 minus 5. What is that angle going to become? 30 minus 5. Try to understand clearly. This total is 30 na. I want this angle. Okay. Once again listen. So this is VRN, this is VYN. What is the angle? 120. This green color, this color splits it as 60. If this is 60, then this splits as 30. So this is 30, this is 30. Now I want this. So what is the angle? So this will become 30 minus 5. Okay, 30 minus 5. Okay, now second thing, I want phi 2. Phi 2 is the angle between what? Phi 2 is the angle between VYB and IY. So that is the angle between VYB and IY. So how to get it? VYB and IY. VYB and IY. That means VYB means what? VYB means what? VYN plus of minus VBN. So this is VYN. So now the resultant of these two, have to get it. The resultant of these two. So the resultant of these two, okay, so this resultant is nothing but VYB. So now the angle I want between VYB and IY. This angle is what? So now if you check this angle I want, this is 30. Why? Because check clearly, the angle between this and this 90, this should be 30. That's 120 degrees. So this is 30, but what I want the angle between VYB and IYN. So this the angle. So this angle will be 30 plus 5. Once again, clearly listen. Let me explain very clearly. What is VYB? VYB means what? This is the VYN. So these are negative side. If I have taken the negative side is nothing but minus VBN. The resultant of VYN and minus VBN is the VYB. VYB is the sum of VYN plus of minus VBN. So that is a VYB. So this VYB exactly 90 degrees to this. So this is 90 means this will be 30. Sorry, this will be 30. This angle will be 30. If you want to check it, or else you go like this. What is this angle? This angle is 120 degrees. Okay, na? This angle is 120. So now this particular line has split as 60, 60. This total is 60. So when this angle is 60, this cuts exactly center 30. But what I want the angle between this green line and this white line, because this is a line current 30 plus 5. So the angle is nothing but how much? 30. So finally I got the two phase angles. Now I can go for the power equations. So what is a wattmeter 1 reading? So let me write here. Wattmeter 1 reading VRB, so not IR, angle between them. What is the angle? VRB and IR angle, cos of 30 minus 5. So please remember these equations, which can be written as VRB means VL, IR means IL, cos of 30 minus 5. This is equation number 1, most important. Next, okay, or else just let me draw somewhat down, okay, somewhat down, because it's going to the very edge, right? W1 is equal to VRB, this is VRB into IR cos of 30 minus 5. This is nothing but VL IL cos 30 minus 5. For 1, let us finish. Let us go for equation number 2, that is VYB to IY cos of 30 plus 5. So this can be taken as VLIL cos 30 plus 5. So this equation number. Understood? So now let me take some expressions W1 minus W2, W1 plus W2, so that I am going to have some interesting relations. Because I want to prove that the wattmeter readings, whatever I am getting, so those summation of these two wattmeters should be equal to the 3 wattmeter. So equation 1 minus 2, W1 minus W2, 1 minus 2, if you take, what I am going to get? VLIL, if I take common, cos of 30 minus 5 minus cos of 30 plus 5, which if you further simplify, VLIL cos A cos B plus sin A sin B minus cos A cos B will minus into minus plus sin A sin B. Okay, I think some terms gets cancelled, this term gets cancelled, so these two terms gets cancelled, and I am going to get here as VLIL 2 sin 30 sin 5. So what I am going to get, sin 30 1 by 2, I am going to get VLIL sin 5. You observe closely, this is the equation for reactive power. Am I right or not? If I write VL is equal to root 3 VPH, here itself we got an expression. So let us keep this as equation number Let's keep this as equation number. Okay, got it? Similarly, if you go for plus, what is going to happen? Plus means the sine terms gets cancelled, and cos 30 means root 3 by 2, 2 root 3 by 2 cos pi, 2 gets cancelled, root 3 cos phi will come. So W1 plus W2, what will get? Root 3 VL IL cos phi I am going to get. So let us keep this as equation number 4. Okay, so 4 important equations dear. First equation is this: VL IL cos 30 minus phi, VL IL cos 30 plus phi. 4 equations, we got it. So now, before entering into the problems, here is I want to write some expressions here. Possible to add one more slide? Okay. Wait. Perfect. Sometimes we get habituating to practice. Yeah, we got the expression now. Now let us move to the next slide. See, what is the slide? What are the 4 equations we got? 4 equations we got. First equation is VL cos 30 minus phi. Second equation cos of 30 plus phi. Third equation is W1 minus W2. Fourth equation is W1 plus W2. So let me write all these equations together. First, W1 equation, I got it as VL cos of 30 minus phi. W2 equation, I got VL cos of 30 plus phi. W1 minus W2 I got as VL sin phi. W1 plus W2. W1 plus W2 you got root 3 VL cos phi. Root 3 VL cos phi. Okay. So now this is, let us take equation number 1 I told you, this is equation number 2 I told you, equation number 3 I told you, equation number 4. Now if you take the relation of W1 minus W2 by W1 plus W2, what you are going to get? One important thing. Okay, before that, let me talk about this W1 plus W2. If you see the W1 plus W2, what is this line voltage? Line voltage can be taken as in relation with phase voltage as root 3 VPH na. So VL is equal to root 3 VPH I can take na. Sir, in star model. In star model, VL is equal to root 3 VPH. IL is equal to IPH cos phi. So for star model, For star model, VL is equal to root 3 VPH, IL is equal to IPH is the answer, right? So now root 3, what happens? 3 VPH, IPH cos phi. So this is what we call as W1 plus W2 reading. If you observe, this is a summation of 3 phases or not. So this is nothing but the 3 wattmeter reading or not. Okay, that means by using the 2 wattmeters, itself, you are able to measure the 3 wattmeters 3 phase power. Actually, by using the 2 wattmeters, what is the reading that you are getting? That is equal to the reading of getting by the 3 wattmeters, yes or not? So this is nothing but a 3 phase power. This is nothing but a 3 phase power. Yes or not? 3 phase power का reading आ गया by just 2 wattmeters. So Blondel's theorem proved. Hence, Blondel's theorem is proved. As per the Blondel's theorem, by using the n-1 wattmeters, we can measure the n phase power. Proved or not? And this is one thing. And the second most important thing here is W1 minus W2 VLIL sin phi. If you observe this, what is this VLIL sin phi? I can write this W1 minus W2. VL is equal to root 3 VPH and this IPH sin phi, which is nothing but the reactive power or not. So this is a reactive power, my dear. So using W1 minus W2, you are getting the reactive power measurement also. By 2 wattmeter method, you are getting the reactive power measurement also by using W1 minus W2. Is it clear or not? So 2 things I want to give conclusions. The summation of the 2 wattmeter readings is equal to the 3 phase power reading, and the subtraction of the 2 wattmeter readings is equal to the reactive power reading. So that is an advantage of by using the 2 wattmeter method. And from this, again, I can do some expressions. If you take 3 by 4, if I am taking the 3 by 4, what I am going to get? 3 divided by 4. 3 divided by 4 means what? W1 minus W2 by W1 plus W2. So what is this? W1 minus W2 by W plus W2. If you check, this will be VLIL sin phi. VLIL sin phi. The whole divided by, this is 3 VPH IPH cos phi. That means, okay, this is root 3 VLIL cos phi. We will write it as root 3 VLIL. So VLIL gets cancelled. So I am going to get this as 1 by root 3 tan phi. So from this, I can write tan phi is equal to root 3 times of, okay, tan phi is equal to root 3 times of W1 minus W2 by W1 plus 2. Understood? So now from this, phi is equal to tan inverse of root 3 times of W1 minus W2 by W1 plus W2. So this is what we call as the power factor. Okay, na? So from this, what is the power factor? The power factor, we can take it as power factor. Also we can get it cos phi, that is cos of this. Understood, all of you? So from this, we can take some extractions. Suppose the phi is equal to 30 degrees. What happens to the readings of the wattmeter? If phi is equal to 60 degrees, phi is equal to 90 degrees, what happens? So based on that, we'll make a table. Okay, so let us go for one table. So let me take a big table here. So first what I'm doing, I will take the phi. Next I will take the cos phi. Okay na? Next I will take the reading of W1. Next I will take the reading of W2. Next I will take the remarks. Okay. So here this is the phi. This is the power factor which is cos phi. And this is the W1 reading. And this is the W2 reading. And these are the remarks. So if we check now, for example, we'll start with 0. 0.5. Yeah, we'll start with suppose 30 degrees. Power factor cos 30. We take W1 reading. See W1, let me take W1 is equal to what? Let me take W1. Let us take readings 30, 0, 30, 60, 90. That is the best. But oh. So let me take this as 0, 30, 60. Okay. Cos phi, unity power factor. This is root 3 by 2. Root 3 means 1.732, that is 0.866. Cos 60, 1 by 2, that means 0.5. Cos 90, 0. Now let us check. What is the W1 reading? W1 is equal to VLIL cos 30 minus phi na. So this W1, this W2 na. So what is W1? W1 is equal to VLIL cos of 30 minus phi. W2 is equal to VLIL cos of 30 plus phi. Now let us see the remarks. When phi is equal to 0, cos 30, that is root 3 by 2. So W1 is equal to root 3 by 2 of VLIL. Positive. W2, 30 minus 0, 30 plus 0, same. So W2 is also root 3 by 2 VLIL. So what is the remarks? The remarks, that means when power factor is unity, the remarks are W1 is equal to W2 and both are positive. These are one expected area. The conclusion which I am talking, this conclusion is only the expected area, my dear. Okay. Next, if you take 30 degrees, what happens to W1 here? So this W1, 30 minus 30, 0, cos 0, 1. So this will be VLIL. This is 30, 30 plus 30, cos 60. That means W2 is equal to VLIL. That means what? One of the wattmeter readings is the other half of the other. Then angle is 30 degrees. Next, if you take 0.5, what I am going to get? Cos 60, 30 minus 60. 30 minus 60 means minus 60. Okay, 30 minus 60 means minus 60. Cos of minus 60 means plus 60. Cos 60 means 1 by 2. So we are going to get here as 1 by 2 VLIL. Next, 30 plus 60, 90. Cos 90 means 0. So we are going to get W2 as 0, my dear. So what is the remark? Remark is 1 of wattmeter is 0. 1 of wattmeter reading is equal to 0. Next, when power factor is 0, that means pure resistive load. Now, this is 90. Cos 30 minus 90. Cos 30 minus 90 means cos of minus 60. Cos of minus 60 means plus 60. So that will become VL IL, and this will be phi is equal to 90 cos 120. This will be minus W2 will be minus LIL by. So one of the wattmeter reading is negative. So what is the conclusion? If you take this 0.5 as a reference, because in the center, if the power factor is increasing above 0.5, we can call as the increasing power factor load type. The power factor is below 0.5 means it is a decreasing power factor load type. So for the increasing power factors, what is happening? The wattmeter readings are going from 0 to positive. For decreasing wattmeters, what is happening? The wattmeter readings are negative. So these are the important conclusions, my dear. So based on these conclusions, you are going to get number of questions. Number of questions are possible. See, what are the questions here? So if the power factor is unity cos phi, suppose if you take the cos phi is equal to 0.5, then what is the conclusion? For 0.5, one of the wattmeter reading will be 0. Anyone, one of the wattmeter reading is equal to 0. Above that 0.5 and below that 0.5, what is happening? Above the 0.5 means positive. Is going for the increasing. The power factor is increasing. That means if you take unity power factor as a reference, cos phi is equal to 1, then what I am going to get? Both are positive. W1 and W2 both are equal and positive. Case studies. And if the power factor is reducing, that means 0.5 to down it is coming. For example, 0 power factor. 0 power factor. 0, 1. I think we are done. Check cos 120 correct enough? 13 plus 9. It's minus 1 by 2, right? So this one for 0 power factor, that means power factor is reducing, then what is happening? One of the wattmeter reading is negative. So try to understand these extractions. So from these extractions, you can guess from the given answers, you can extract some answer from the given question. Okay, my dear, these are the extractions. For unity power factor, we are getting the positive wattmeter readings, and for reference, if you take the reference 0.5, you are getting the 0, one of the wattmeter. And at 0.5 you take reference. Above 0.5 the wattmeter readings are positive. At 0.5 one reading is equal to 0. Below 0.5 one of the wattmeter readings is. These are the most important extractions, and this table is one of the important table, my dear. Please make a star for this particular. Please make a star for this particular. This shows the complete understanding of the 2 wattmeter. So what I have proved, by using the 2 wattmeter, you are getting the same power reading which you have got using 3 wattmeters. That means 1 wattmeter is saved. 1 wattmeter is saved means how many connections saved? 1 pressure coil connection, 1 current coil connection, 1 RSC connection is saved, na? So that's what I have shown you in the beginning. In the beginning of the lecture, when you are using this many wires means, see, this many wires means, second, I have one slide over there. See, in 3-phase 4 wire, if I am using RYBN, I require W1, W2, W3, but in 3-phase RYB, we require what? Only 2 wattmeters. We require only 2 wattmeters. Okay, the number of connections have been reduced. The number of connections reduced means like economical. The cost reduced. The cost reduced and the economics are improved. That means financially it is good. And the transmission losses, the copper losses, everything is reduced by using the 2 watt meter method. So if I'm using only 2 watt meters, then how many connections are reduced? These 3 connections are reduced. So 6 components only. 6 components. 2 current coils, 2 pressure coils, 2 RSC resistors. 6 components. So that is what I want to talk about. Okay, my dear. So please extract these conclusions. The conclusions are important. Derivations nobody can ask you, but the conclusions are very, very important. Conclusions are very. Okay. So now with this understanding, now we can start the problems. So please take this table as a reference table. From this table, now we'll move to the numerical. So up to now we have discussed the 2 watt meter method for star model, lagging power factor. The same thing you can go for the leading power factor and other things, but not necessary here. One is enough because we have extracted the expression of tan phi, or phi is equal to this expression. Tan phi is equal to root 3 W1 minus W2 by W1 plus W2. Anything expression you can remember it. Any expression you can remember. Okay, my dear. Now we'll move for the problems. Now we'll start the problems on the 2 watt meter method. Let us see the first question. A dynamometer type watt meter responds to the dash. Option A, average value of the active power. Option B, average value of the reactive power. Option C, peak value of the active power. Option D, peak value of the reactive power. So how to do this? This question was asked in IIT Madras 1997 GATE examination. As all of you know, the deflection torque in the dynamometer is given by formula I square dm by d theta, where I is the current, but we are having 2 coils, current coil and pressure coil, so that we can divide into I1 into I2 dm by. But when you apply the concept of pressure coil and current coil, so this will become VPC by Z cos phi dm by d theta. So this was our equation. Deflection torque is proportional. Actually here it is coming like this. So that means if you take the deflection torque expression, so this one, here I have taken. So this will be taken as VPC ICC cos phi into this one, we can take it as 1 by Z dm by d theta. So now if we check this power, okay, so this is the power equation. So TD is proportional to the average torque. It is proportional to the average torque. VPC ICC cos phi. So that is the active power. So that is also called as average power. So the right answer for this question is average value of the active power is the right answer. Question number 1, right answer is option A is the right answer. P average. Now let us move for the next question. Question number 2, IIT Bombay 1999 question. How to answer this question? The phasor of a circuit 10-15 degrees and the current phasor is given as 2 minus 45. The active and the reactive powers in the circuit are dash. As we know, S is the apparent power, P is the active power, and Q is the reactive power. As we all know, S is equal to square root of P square plus Q square. Am I right or not? Or if you take in the normal format, P plus J Q, that is the representation. So I can write S is equal to P plus JQ. So this is the apparent power. So this is the active power. So this is the reactive power. So now from the given data, what we can take? The given data is given as voltage phasor is given as 10, 15, 10 with a phase angle of 15 degrees, and current phasor is given as how much? Current phasor is given as 245 degrees, 2 with an angle of 45 degrees. So what is the question asked? So power they are asking. So power is equal to, how to write it? Power is equal to the active power, reactive power. How to do it? So that we can write it as the apparent power. The apparent power will take the magnitude, that is S VPH IPH. If you take the magnitude of the phases, just magnitude of the phases, we'll take positive deflection 15 plus 45. So that will be what? This is 10 into 2 with a phase angle of 60. So this is 20 watts with a phase angle of 60 degrees. So now if you write this in A plus JB format, if you write this in A plus JB format, e power j theta, so what we can write it? How to write it? So this one we can write it as 20 cos 60 plus j 20 sin 60. That means this represents as 1 by 2 and this represents as root 3 by 2. Okay, so what is the value we got it? Apparent power S is equal to 20 into 1 by 2 plus, this is J, 20 into root 3 by 2. So now what happens here? So this will be 10, this will be 10. So S will be 10 plus J 10 root 3. So this is A plus JB. That means we can take it as this as the P and this as the Q. So this is the S. So S is equal to what, my dear? Apparent power S is equal to this 20 watts. S is equal to apparent power, that is 20 watts, and the active power, that is 10 watts, whereas Q, reactive power, that can be 10 root 3. 10 root 3 means 1.732 into 10, that means 17.32 volt ampere reactive. Okay, so this is some VA, we can take it. So question asked is P and Q, 10 watts and 17.32. VAR is the right answer, volt ampere reactive. So the answer for this question will be 10 17.32. So 10 17.32. So that is the first question, option A. Very good question, very fundamental questions. Those who are electrical students, they know very well about the apparent power, active power, power factor, and real power. Okay, reactive power. Now let us see the next question. Yeah, question number 3. This was asked by IIT Kanpur in 2001. Very simple question. The minimum number of wattmeter or wattmeters required to measure the 3-phase, 3-wire balanced or unbalanced power is dash. So according to Blondel's theorem, for an n-phase balanced or unbalanced system, n minus 1 wattmeters are enough required. So for a 3, the minimum is 2, not 1. Use 1, you cannot get the full reading, you can get only one reading, W1. So minimum number of wattmeters required is 2 wattmeters are. Let us go for next question. Yeah, what is this question? electrodynamic type. What is this question? Electrodynamic type wattmeters. Just wait. Which this place? Correct. After this comes base comes. Yeah, see this question number 4. Electrodynamic type wattmeters have large errors while measuring power in AC circuits at low power factor conditions. Yes. Since the voltage across and the current through which coil is having error. See, the errors are majorly due to what? The errors are majorly due to, so we expect is the current passing through the pressure coil, yes or not? And this is the current passing through the, sorry, let me write in a, so this is the current passing through the pressure coil, and we expect this is the voltage in the pressure coil. So this is a current passing through the pressure coil, the voltage in the pressure coil, and the angle between them is, we expect 90 degrees, but it is possible if the pressure coil is purely inductive. But as I told you, definitely it cannot be. So there exists an error. Okay, so this is the current passing through the pressure coil. So this error only we have taken it as, this angle only we have taken it as delta. Okay, so the reason for this question is, what is the reason for the errors? Error is due to what? Current coil are not in phase. So the voltage and currents of the pressure coil, voltage and current of the pressure coil are not in 90 degrees phase shift. That is the point. So the right answer is pressure coil related. So option C is the right answer. That is the reason why we are getting the error due to pressure coil inductance. Okay. Next, yeah, how to solve this question? We'll do one thing. First, we'll solve these objectives, and yeah, first let us take question number 6. Two identical wattmeters are connected to measure power in a 3-phase, 3-wire balanced load. The load power factor if W1 is equal to W2. How to solve? So the fundamental formula we have, what is that formula? All are formula related, but actually without formula also we can tell. What is that? Without formula also we can tell. W1 is equal to W2, we are getting in a table, right? So we got some table, right? I have given a table, yes. If you see this slide, so W1 is equal to W2 is happening when the power factor is unity, yes or not? So that was a question asked, and one of the wattmeter reading is equal to 0. That is happening when the power factor is 0.5. So if you can remember directly this bit you can answer. So question asked here is this question, what they asked, question number 6. W1 is equal to W2 is happening what? So this is happening at what? Phi is equal to 0. So this is the unity power factor. So power factor will be unity. Power factor is equal to either W1 or W2 is equal to 0. Then the power factor is 0.5. That already from the table. I want to show you the slide number. I want to show you in the slide. We already taken a table. Okay, so two wattmeter readings are equal when this is equal to unity power factor, and one of the wattmeter reading is equal to 0.5 whenever one of the wattmeter reading is equal to 0 whenever the power factor is equal to 0.5. Sir, we cannot remember this in the exam, then what to do? If you can't remember this in the exam, you can go for derivation. How to do the derivation, that I will explain. So as you know, the fundamental formula tan phi, this formula you can remember as a √3 into W, or you can go for this formula cos phi. First formula W1 is equal to VL IL cos of 30 minus 5. W2 is equal to, you can take it as VL IL cos of 30 plus, like that you can take it. So now what is question? W1 is equal to W2, then how to answer? W1 is equal to W2 is possible when phi is equal to 0 directly, yes or not? So when phi is equal to 0, if you take, automatically W1 will be equal to, or you can take W1 is equal to W2 situation. If W1 is equal to W2, we'll go in a reverse way. If W1 is equal to W2, so what we can take, VL IL cos of 30 minus 5 is equal to VL IL cos of 30 plus 5. It's cancelled. Okay. So cos of 30 minus 5 is equal to cos of 30 plus 5. Cos of 30 minus 5 is equal to cos of 30 plus. When it can happen, or phi is equal to 0, it can happen. So power factor is equal to cos phi is 1. Okay, first question answer is unity power factor. Similarly, second question also you can do it. Any one of them is equal to 0, you can take it. So W1 is equal to W2 if this is the situation, and either one of them is equal to 0. So W1, second question, B question you can answer. So B question you can answer. W1 or is equal to W1 if you take 0, or W1 or W2 let us take 0. So this is a VLIL cos of 30 minus 5. So directly you can see the picture and you can tell 30 plus 5. When phi is equal to 60, then what happens? W2 will become 0. So phi is equal to 60 means what is the cos phi? So that is a power factor, cos 60 is equal to that is the way. If you are able to remember, that is enough. I told you how to remember also. How to remember that? I told you by this table. How to remember with this table. So you can take the 0.5 as a reference. Take the 0.5 power factor at 0.5, above the power factor and below the power factor. So below the 0.5, one of the wattmeter will be negative, and above the 0.5, the wattmeter readings will be positive. Okay. Let us move for the next question. Question number 6. 2 wattmeters which are connected to measure the total power on a 3-phase system supplying a balanced load read 10.5 kilowatt and minus 2.5 kilowatt respectively. The total power and the power factor respectively are dash. So what is the data given? So W1 is given as 10.5 kilowatts. W1 is given as 10.5 kilowatts and W2 is minus 2.5 kilowatts. W2 is minus 2.5 kilowatts. So W1, W2 is given. Then the total power and the power factor, how to get it? See here, what to do it? If you take the total power, that is 10.5, 2.5, so that is a 8 kilowatts. What about the power factor? How to get it? So we know the formula of tan phi, right? Tan phi I will use, that is root 3 into W1 minus W2 by W1 plus W2. Okay. So now we can substitute here. This is the root 3. W1 is 10.5 kilowatt minus W2 is minus 2.5, so that will become 2.5 plus, and this is 10.5 and this is minus 2.5. So what I am going to get, this is root 3, 10.5 plus 2.5, that is how much you are going to get? So that is a 13 divided by, this is 8, right? 13 divided by 8 into root 3. So it is coming as 2.814. 70.44 is the phi. Okay. So from this, what I'm getting, I will go for the next step like this. Okay. So this is the tan phi. So if you simplify from this, the phi is equal to 70.4. But the question asked is a power factor. The power factor is equal to cos phi. So cos of answer, we are getting it as 0.334. 0.334. So this is the power factor, and the total power is W1 plus W2 is the total power. The total power is equal to W1 plus W2. Okay, na? So what is the W1? So W1 is 10.5. W2 is minus 2.5. So 8 kilowatts is the total power. So option is the 8 kilowatts is the total power. 8 kilowatts is the total power, and this is 0.334. So 0.334 and this 13. Option D is the right answer, right? Eight kilowatts and 0.334. The right answer. Option D is the right answer. Okay. Next. What is this question? Question number power. Yeah, question number 8. Let us see. Power consumed by a balanced 3-phase 3-wire load is measured by second here. 1 second. Question number 8. Let us see this question number 8. Power consumed by a balanced 3-phase 3-wire load is measured by 2 wattmeter method. The first wattmeter reads twice that of the second. So W1 reads twice of the other. Then the load impedance angle in radians is dash. That is a power factor angle. So what we can write here directly, we can go with tan phi is equal to root 3 times of W1 minus W2 by W1 plus W2. So this one I can write it as, okay, so W1 is equal to 2W2. So this one I will take it as 2W2 minus W2 divided by 2W2 plus W2. Okay, so this will be how much? Root 3. So this is the W2 and this is the 3W2. Okay, so this will become 1 by 1 by root 3. So tan phi is equal to 1 by root 3 means phi is equal to tan inverse of 1 by 30 degrees, right? 30 degrees. Degrees. 30 degrees is the this one. Question asked is what? Okay, radians. Oh, he's asking the radians. So this is degrees. So how to convert degrees? 360 degrees is equal to 2 pi radians. Okay, so 1 degree is equal to pi by 180 radians. So he's asking the 30 degrees. So for 30 degrees, pi by 180 into 30 radians. So the angle is pi by 6 radians. What is the correct answer? The correct answer is pi by 6 radians. The right answer for this question is pi by 6 radians. See the right answer. See, pi by 6 radians is the right option. Now we'll move for the question number 9. Let's see. Question number 9. While measuring the power of a 3-phase balanced load by the 2 wattmeter method, the readings are 100 watts and 250 watts. The power factor of the load, like I said, formula tan phi is equal to root 3 W1 minus W2 by W1 plus W. So root 3 W1 is 100 minus 250 by 100 plus 100 minus 250 divided by 350 to root 3 shift minus 36. So from this what I am getting, phi is equal to minus 36.58. That is the question asked. The power factor is okay, power factor is cos phi. So cos phi is the power factor. It has 0.8. The right answer for this question is 0.8. So first I want to complete this formula based. Why? Because see how many number of times the formula based questions came. That's why. You remember the formula, easily you can answer. Otherwise it will be. That's what the conclusion. GATE reads the conclusion. How it came, how the derivation came doesn't matter. But for a faculty we have to teach everything. So, but please take the conclusions and you practice it. Okay. Next question. 2 wattmeter method is used for the measurement of power in a balanced 3-phase load supplied from a balanced 3-phase system. If one of the wattmeter reads half of the other, then the power factor of the load is dash. So W1 is equal to half of the other. Anything you can take it. How to take it? When it is possible. Both are positive. One of the wattmeter is positive, means definitely it should be reference point 0.5 power factor above 0.5. Like that you can remember. So below 0.5 whatever is there, but all are above 0.5. I told you power factor 0.5 you can take as a reference. Above the 0.4 power factor whatever are there, that is the increasing power factor, and below the 0.5 whatever there are a decreasing power factor. Yes or not? So keep that in mind. So now what to do it? W1 is equal to half of the W2. So how to do it? Or W2 is equal to half of the W1, anything it can be. In that situation, better you go for this formula. Don't confuse about that formula. So VLIL cos of 30 minus 5 and W2 is equal to VLIL cos of 30 plus 5. Suppose if I am taking W1 is equal to half of the W2, then what I can write? VLIL cos 30 minus 5 is equal to half of VLIL cos of 30 plus. So this gets cancelled. So 2 cos 30 minus 5 must be equal to cos 30 plus 5. What is possibility now? For phi is equal to 0, not possible. For phi is equal to 30, not possible. Is possible? For phi is equal to 30, if you take 30 minus 30, 30 minus 30 cos 0, 1. So 2, 30 plus 30 cos 60 by 2. Not possible. Phi is equal to 90, not possible. Phi is equal to 60, not possible. So what is possible then? Check. W1 is equal to half of the W2. Okay, we'll take minus 30. Take minus 30 also not. If you take minus 30, it is possible. If phi is equal to minus 30, then what happens? This will be 2 cos of 30 minus 30 means plus 30, and this will be cos of 30 minus 30. So this will be 1, and cos 60 1 by 2. So this will be 1. So the right answer is phi is equal to 30. Like this we can do. Phi is equal to 30 we can do, or we can also do with other method, the tan phi method. Tan phi is equal to root 3 W1 minus W2 by W1 plus W2. My dear students, he has given like this. In this situation, what we can do? So if you take, we are getting negative, right? I think tan of negative we are getting. So anything, okay, you take half of the W2 minus 1 W2, half of the W2 plus W2. So this will become what? Root 3. This is minus half of the W2 by, this will be 3 by 2 W2. Okay. So W2 gets cancelled. So minus root 3, that means minus 1 by root 3 we are going to get 1 by 2, 2 by 3, 2 gets cancelled, 1 by 3, 1 by root 3, minus 1 by root 3. That means phi is coming as minus 30 degrees. So cos phi, cos of phi, that is cos 30, because cos of minus phi is equal to cos phi, cos 30, 1 by cos 30, root 3 by 2, root 3 by 2 means 0.866 is the answer. Right answer is very good question. Option D is the right answer. See, I know the derivation, I know everything, but in the exam, if you do not apply the formula on time, and by applying the formula also while taking the calculation, if you do a silly mistake, you are going to lose the question. That's why better to do cross verification. Better to do the cross verification like this. Okay. So this is the expressions, my dear. So don't forget these questions. Very good questions. Yeah. What is this question? Let us see. This question is related to error in the connection, error due to connection. The circuit in figure is used to measure the power consumed by the load. The current coil and the voltage coil of the wattmeter have 0.02 and 1000 ohms resistance. So this is a current coil and this is the potential coil. So current coil resistance is given, potential coil resistance is given. The measured power compared to the load power will be dash. Measured power compared to the load power will be dash. So how to do it? So what he has given, so this is the ICC. If we check the ICC, how much is the ICC? That is a 20 amperes. ICC is 20 amperes. Next, if you see the resistance of the current coil, the resistance of the current coil is how much? Resistance of the current coil is 0.02 ohms. So this is 0.02 ohms. Next, voltage in the pressure coil we don't know, but the resistance of the pressure coil is given. Resistance of the pressure coil is 1000 ohms, and this is voltage across the pressure coil. We can take it as 200 volts. That is a 200 volts. Now what is the question he has given? Let me check it. Unity power factor. So cos phi is equal to 1. Now if we check the question, what is this connection? This connection is what? The pressure coil is connected at the current coil side. That means it's connected at the mains side, not at the load side. So that is what we call MC connection. What we call it is, we call it as the MC connection. So now which is the coil connected to the load? The current coil. That means in addition to this true value, we are going to get this a load true value actually. So in addition to this, we are also going to get the measured value. So what is the true value? Let me write. The true value of the power is equal to WL, which is nothing but VL IL cos phi. So the voltage across the load is given as 200 volts. So that I will take it as 200 into IL is what? IL is nothing but ICC. Why? Because the same current will travel here. Yes or not? Whatever the current passing through the current coil, the same current is traveling. So this is the 20 amperes, and the cos phi unity power factor, it is going to become 4. Cos phi is how much? Yes, unity power factor. Unity power factor given na? Yes, unity power factor. So that is going to be 4000 watts. But the measured value will be what? Measured value will be what? This plus, in addition to this, there is a power across the current coil. Yes or not? Power in the current coil. So that I can take it as power due to current coil. Okay. So how to write it? That is this plus current passing through the current coil to resistance of the current coil. So we can do it. This is the 4000 plus current passing through the current coil, that is a 20 amperes. So this is a 20 amperes. So 20 square. Resistance of the current coil. Resistance of the current coil is 0.02 ohms. So this is 0.02 ohms. So how much it is going to become now? So 20 square into 0.02, 8 plus this. So this is 4008 watts. What you are getting? 4008 watts. So the true value is 4000 watts, and the measured value is 4008 watts. Okay, question asked is what? I think he asked the percentage error. Yes, percentage error. Always remember, in LC connection or MC connection, the error is due to the coil which is connected to the load side. So this particular coil is connected to the load side. Okay, so that is a possibility. So what we can take now? So percentage error we have to take. Percentage error means measured value minus true value divided by true value into. So what is the measured value here? The measured value is 4008 minus true value 4000 divided by true value 4200. Answer is 4008 minus 4000 divided by 4000 into 100. So that is coming as 0.2% more. 0.2%. That means positive. So measured value is 0.2% more. The measured power is definitely more na. True value is this. This is the true value. But the measured power will be what? This plus power due to the current coil. That is the measured value. Definitely measured value will be more. That is what the error. So the right answer is 0.2% more. 2% more. Very good. This more or less is also very logically asked. Measured value will be definitely more. In addition to the load power, it is also measuring the power current coil. Okay. Are the let us see this question. Question number 5. How to do this? So if you see, diagram is given. Sometimes the questions are asked like this: RYB sequence. W1 is connected between the R and the Y. So this voltage is the VRY. And W2 is connected between V and Y. So this voltage we can take VBY or VY. Okay. So what are the questions asked? The line-to-line input voltage to the three-phase 50 Hz AC circuit is shown in the figure is 100 volts RMS. So the line voltage is given as 100 volts RMS. Okay, next. Assuming that the phase sequence is RYB, the wattmeter would read as dash. So what is this question? So first of all, if you see, this is VL and in star model, is a star model. So for a star model, VL is equal to root 3 VPH. Am I right? VL is equal to root 3 VPH. So from this, if I want to know the VPH, VPH will be VL by root 3. So that is going to become 100 by root. I got the VPH. Next, I can take IPH. IPH means VPH by ZPH. VPH by ZPH. So this VPH is 100 by root 3. And from the picture, if you see the ZPH is 5 ohms. All the magnitudes are 5 ohms. So we can take this as 5. So this will become 20 by root ampere. 20 by root. So we got now what is the W1? W1 is equal to VL IL cos of 30 minus 5. So for a 2 wattmeter method, so what is the W1 reading? VL IL cos of 30 minus 5. W2 is equal to VL IL cos of 30 plus 5. As it is a star model, the VL is equal to root 3 VPH we can write here. Next. Okay. And IL is equal to IPH we can write here. Cos of 30 minus 5, the power factor angle is also given. And this is also same, root 3 VPH IPH cos of 30 plus 5. Definitely one of the wattmeter reading is going to become 0 because one of the wattmeter reading cos 60 means 0.5. 0.5 means the reference, at reference, one of the wattmeter reading 0 we have discussed. Okay, so how to do it now? So what is the answer? So if we take the W1, what is the W1? We got it, root 3 VPH IPH. So this one I can take it as root 3 VPH IPH cos of 30 minus 5. So we can take it as cos of 30 minus 5. So if you take this root 3, what is the VPH? VPH we got it as 100 by root 3. Substitute it 100 by root. And IPH, how much we got it? IPH we got it as 20 by root 3 amperes. So these are 20 by 3 cos of 30 minus, how much you are going to get? Is 100 into 20 divided by root 3. Cos of 61 by 2. We had a mistake. VPH is 100 by root 3, which is VPH by ZP. Says we have done a mistake here. This phase current is definitely having the 560, right? Definitely here it will be minus 60 coming when it comes to top. But we will take the positive deflection directly. We can take from this VL is equal to 1000 means what is the IL? IL is equal to VL by Z, line to line impedance. So this is going to become 1000 by 5, 100 by 5, that is equal to 20 amperes. Correct only. 0.54. Yeah. Correct. This is 100. Perfect. Cancel this step. Check here. Check. Now if you check, this is 100 to 20. Cos of 30 minus 60. Cos 30. Cos of minus 30 minus cos 30. 100 by 2 root 3. This is root 3 by 2. It's cancelled. So answer is 1000 watts. So this is W1. At one of the wattmeter it gets negative. So one of the other wattmeters, what? W2 is equal to root 3 VPH IPH cos of 30 plus 5. This 5 if you take 60, so this will be 0. One of the wattmeter reading is 0. You can take W1 that and W2 this. He has taken that. So one of the wattmeter reading is equal to 0. So definitely we can go for this option. You understand? Right answer is option C is the right answer. Option C will be the very good question, qualitative. Option C is the one of the wattmeter reading is equal to 0 because the power factor is 60 cos phi 0.5. So cos phi 0.5 means you can go for the table. You go for the table. Go for the table. One of the wattmeter reading will be 0. Any one of the, as we have taken W1 as VLL cos phi. When it is 0.5, this is the okay. That's it. We completed the questions. Okay, my dear. So these are the variety of questions I have solved. So from these questions, please try to practice more questions on the 2 wattmeter method. Most of all the questions are on formula based. But remember how to apply that formula don't forget. Okay, na? So I wish you all the best. We'll meet in the next lecture. Thank you.